Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Welcome back. We're looking at example E4.3.1 internal design pressure for a cylinder shell, and this is part of the problem sets that are available in ASME PTB-4, and it all has to do with Section 8, Division 1. So let's jump into this. So as we said, we're going to abbreviate that. We're going to call it 8-1 instead of writing this big sentence out here. And then the other one we'll look at is the Division 2 as it pertains to Division 1. As you recall in the previous PDBs, Code Case 2695 allows for use of some of their calculations for Division 1. And but also you need to check with the local authority when you do, if you decide to do this. But I don't mind doing a bit of it just as a verification, but I rarely see this done. But needless to say, it's allowed. So let's continue, and we're going to work on the first one. Calculations are based upon UG27 for internal pressure. And, this is a post 1999 model. We're using tough carbon steel materials. And we have our diameter shown there, corrosion allowance, the type of welding we're doing, and the inspection level, which is 100% RT. There's no post-weld heat treat requirements except maybe by code, but when we do the thickness calculation, we'll be able to figure that out. Our pressures are fairly high for a size this large. It's 356 psig, and we're at basically 300 Fahrenheit or 150 degrees or centigrade. So let's jump into more details. So before I added these slides because the examples are a little bit brief, and it kind of challenges the engineer to go look through the code to more understand this. So there is a section in UG27, it's part C, and for the it's very well organized. So for the different types of shapes, they have different sections. So part C is the section we're interested in, and they say the minimum and thickness or maximum allowable working pressure. So you can see there by 1 that they've got, an equation written in terms of the thickness, or if the engineer wants to design for the pressure. So it's interesting because if you, the software will, you select your components and it will figure out your weakest link. So then you calculate your thickness you need, and you go back. The computer's software like Compress will go in and put your calculated thickness in there, and then figure out where your pressures are, like for the other components. And so this is, one of the reasons why they have these two arranged this way. Now there's a couple things here. When the thickness does not exceed 1/2 of the inside radius, okay, and P does not exceed 0.385 SE. These are rules going back to strength of materials, and what they're applying is the Hoop stress equations, which is thin wall theory. And so it's called a biaxial stress. So the stresses are acting on, in 2 planes, not in 3 planes. And of course we have the circumferential longitudinal stress, which is, and then we have the longitudinal stress. And if you look at the bottom of this equation, right, you can see that this should be smaller than that, right? So let's continue this. And of course the same rules apply about you have to check in your spread and build that into your spreadsheet, by the way, so that you can verify those. So if you go to G, E, F, and G, when necessary, vessels shall be provided with stiffeners. Okay, that's one of the rules. And you have to go to UG22, which will be a focus of perhaps a future video. We'll go into extreme depth into stiffeners if there's interest. And then we want to, if we have like jackets, steam jackets around the cylinder, then there's special requirements under UG47C. And any reduction in thickness within the shell cores, because of, rolling or like bending kind of thing, then you have to look at UW9. So you just can't just go ahead and do the calculation. You have to consider other variables. So let's go to UW12 because it talks about joint efficiency. And recall earlier that we determined that it was a type 1 category joint, like a category weld, which is described as a butt welded on both sides or from one side. In our case, it's from one side without a permanent backing strip. And nowadays, 20 years ago, I saw a lot of backing strips. I don't see so many anymore. I'd love to hear from you, your experience of the use of backing strips. But anyway, so they have to be, it says also that they are verified as having achieved full penetration and fusion as required by UW35. So this is, like kind of a rabbit hole. You go jump to here, to here, to here, and that's the code. And the more you work at the code, the better off, the more you'll get used to it. And so we learned earlier that we're looking at, category A and type B weld joints. So in our case, we're looking at a full RT, so our joint category is 1. So let's drop all this into here. So, in the previous slides, we went the previous presentations, we went through how we get the allowable stress. And of course, that's always the hot allowable stress, as I call it. And so you need to go into section 2D, table 1A, which is for ferrous materials like this SA 516 grade 70N material. And then in this case, example, we didn't have any head in this tank because perhaps it was a gas, but in this example, you'd have to make that adjustment for the hydraulic head, and you have to go to the very bottom of the vessel and assume the vessel's totally full. This is then sort of the normal case. So in this case, we've adjusted it. It's 356, it's unchanged. And of course, there's an adjustment also for a dimensional adjustment, and of course it's half the inside diameter plus the corrosion allowance. So we always work with the corroded diameter when we do our calculations, okay, to get the more consistent answer. I mean, it's not very much, the corrosion allowance, but it's important to have reproducible results. So then now we're going into method 1, which is described in the PTB. And option 1, we have a full RT and a cylindrical shell, circumferential stress. We do our first check, as we mentioned earlier, where we check our thickness is less than a quarter of that, and all I did is I wrote a if-then statement, and also the pressure has to be less than the allowable stress, times the joint factor, which is 1. And then once that's valid, then you go ahead and you can use UG27C1. And so when we go in there, you get 0.812 inches. And you adjust for the corrosion allowance, you get 0.93. And if you were to go to the nominal allowance, you're probably looking at a 1-inch thick plate for your nominal. But for this purposes, we didn't make that adjustment because sometimes you can order the plate a little bit closer from the mill. So now we look at the longitudinal stresses, and you can see when we do the equation, we get roughly half, which is what we'd expect. Some people, they just jump to the circumferential stress. And anyway, so we go through the same exercise, a slightly different equation, and we get 0.52. And of course, we have to take the maximum. So we get 0.937, and that's all there is to it. So let's continue here. So what are the limitations? Well, there's an appendix 32 called local thinning that you have to be aware of when working on that. So the fabricator has to make sure that they meet those requirements when they're forming. And there's also a minimum thickness as well. Like if you, depending on your material, there's a minimum thickness requirement. You can't make it the thickness of a pop can. The code won't allow you to because of scratching and so on. It has to be somewhat robust. And then under tolerances, and a lot of that is built into the under tolerance is built into the plate specs when you buy the plate specs. But you need to be aware of that, these issues. And of course, the corrosion allowance, which we added to that issue. Okay, so let's continue through this. We looked at this Division 1, and now we're going to look at this code case 2695, and we'll continue here. So once again, we're going to set up our outputs just to get everything ready. And in this case, they work with the diameter. And so that there's the adjustment there, very similar. It's just a geometry thing. What else can we say? We'll use the allowable stresses, always the Division 1 allowable stresses when we do the Division 2. And if you look at some earlier videos, we had this sort of a description of what 2695 will allow. And so take a look at that. It's one of the earlier episodes. So let's look at this calculation. So the calculation is shown there, and basically it's a more exact calculation because it takes a little bit closer, more accurate interpretation of the hydrostat, like the pressure in the vessel. And so that's why they have that exponent there. And so anyways, you get 0.935 using that equation after you adjust for the corrosion allowance. And then we'll go to the next slide and we will summarize this. So our conclusion is that the required thickness for Division 1 and 2 are exactly the same. And perhaps you'd want to use Division 2 to just double check your Division 1, which is what I do. I rarely do Division 2, but it's in your toolbox, and ASME allows that. So that's why we're talking about it today. Anyways, I hope you enjoyed this video.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.